Everyone knows Misha Gromov. He's a spectacular mathematician and a very interesting person as well. And I know that he's been doing this work, thinking a lot about the way mathematics can interact with not the usual subject, but things like neurophysiology, life, et cetera, et cetera. So I think we're going to enjoy this talk very much. Misha, thank you.
Yeah, of course. So I'll try to entertain you. My pleasure to be here. And so you see these pictures, and you see this quotation, and because you're in Canada, you know French enough to understand it. And by the way, because you can see, again, it's hidden when and who said it. And you have some guess, yeah? And it was said about 300 years ago by Buffon, and it equally applies to life and to cognition. And this is the subject of my talk. And the point, yes, in this picture is that you see difference between life and non-life. On the left-hand side, you see Martian picture. It's void of life. On the right-hand side, in the center, you have definitely something alive. And do you recognize what are these numbers? Typing 1828, 1828. You know what it is, you know? So 1828, 100. 1820, it was birthday of Leo Tolstoy. But some accident, it's also the beginning of the E number. And they have two strange pictures from abstract point of view, the point of view of Martian, on somebody who never saw life. If you see these two pictures, each of them look completely a random configuration of dots, whatever, and appearance, probability of each of them, you know, how many pixels are there. So it is well, of each of them well above Google. However, if you see one, then the relative probability of reading another become small, but not that small. Maybe one over several quadrillions, but not infinitely small. So when you see one pattern of life, another may come along. And that, my point that life and cognition, our cognition is continuation of life, and we have to, the point is to start as a mathematician, think about it. By the way, here is another quotation. It's another, actually, Frenchman who said it. It was about 100 years after Buffon. And this man didn't follow this wisdom expressed in these words. And this was Napoleon Bonaparte. He was one of the cleverest men who ever lived, but he made also the cleverest possible mistakes. Now, what is life? So biologists, sometimes some of them very much concerned to give a definition. When they say definition, they want to give necessary and sufficient condition to life. And this from, well, as kind of mathematicians, we don't know much biology, but we know something about definitions. And we know definitions don't come cheaply. And great definition were invented, given by great people like Grothendieck, who defined algebraic curve, not in a way people would do it. And as was tried people before, also great mathematicians like Haraway couldn't give the right definition. We don't know if the definition by Grothendieck is the best, but it was difficult to come. So, and these only words which you have to remember, which said by biologists about life. They would love Darwinian evolution. They say far from equilibrium, following Schrödinger. It's not in usual biological lexicon. And then there are compartmentalization, self-replication, and metabolism, reflecting different aspects of life. And well, you can say, well, that's definition of life, or kind of, yeah. But what is behind these words? And just before going to that, see what we say, what we know about cognition. And this is a poetic picture of cognition. And this picture was known about 5,000 years ago by kind of what somebody called Imhotep, half mythical kind of figure. And we never have records of what he written, but it was done by people about several, I think, 1,500 years after that. And there was a Galen who definitely made experiments showing that our thoughts, our actions at least, are governed by the brain rather than by heart, as was believed by Aristotle. But what exactly how it happens, how the brain produces thoughts, there was nothing has been learned to the last 5,000 years. Kind of zero from certain point of view. Of course, there were elaborations. So if you look at this, I can show you a bigger picture in a second. Okay, so you see it. Now, psychologists tell you a lot, they believe this a lot, but of course, it is nothing that would surprise Galen or even Aristotle. They say, well, maybe this, but this is just words, words, and words, and there is little substance to that. That's how it just not something very original, it's just common sense. But if you look, so what happens to biology, it will be a completely different story. And what's behind these words on here, it's lots and lots of stuff. And so I'll show you the pictures just to see the basic objects to which this applies. So what is this system without out of equilibrium, non-equilibrated system, metabolism, evolution, doesn't apply to cows. It applies, of course, also to cows. But for biologists, life starts with the cell, and cell are the units of life, and nothing of the kind was known even to this level even 200 years ago, right? And each of them is kind of an elaborate machine, elaborate thing, and each word here, it's a volume of knowledge behind it. Yeah, it's not just to understand the function and the meaning and the role of each object here. It takes several lectures, and certainly none of that would be understandable before people know basic chemistry, physics, and which was certainly unknown to ancients. Now, still, what is difference from kind of physical and biological point? Maybe I'll be better to remove. Let me see, this is too big. Yeah. What is the difference between physics, chemistry, and life? Or what is that? And physicists and chemists and now computer scientists have their definitions of life. But we don't try to define life. It's not our business, but we want to develop a language which will essentially use the same words that biologists do, but just try to make it precise, borderly as precise sense, and which incorporates what is there. So we don't invent anything new, but just to say it in a kind of systematic way. So as mathematician, we can participate in this feast of observing and enjoying the beauty of life and cognition. And cognition, of course, our thinking as mathematicians is part of that. And this in particular want to understand. So what happens in our minds? And so, but for that, to start understanding that, we have to have at least superficial knowledge of biology. And this superficial already is a lot, right? Because biology is a big subject. So, and the major ingredient, new ingredient, when we speak about biology, is concepts of information and everything related to this. But this is not a mathematical kind of information. You know that Shannon information, and it's just some number which usually incorrectly defined by mathematicians, or incorrectly defined by physicists, by the way. But it is something else which has no precise definition in mathematics because we don't have the domain where to define it. For example, if you compare with algebraic geometry, where definition of algebraic variety by Grothendieck only possible in the language of categories, starting with categories of commutative algebras. We don't have this ambience yet, where you can define something more specific like information. This mathematics is to be created. And just I just to show that there is enough structure inside of biology, I hope that to create such a mathematical perspective on that. It's already there. We just have to absorb it and turn it in a more mathematical way. And so this information. And so something was written I don't want to repeat. And there are two different kinds of informations. And it's program and signal. And that's all present in biological concepts. And immediately that brings concept of biological structure, biological function, and purpose, especially purpose, which is the word which is impossible in the physical language or chemical language. So biological system, you can say it's physical system, but it is completely kind of irrelevant. Yeah, its physicality or even its chemistry is just closing for that, or maybe like it's not as essential as nature of the chemistry of the fuel you run your engine. The question is what the engine is, what it does, and what is its structure. And then, so this information, it's something about we can share speak, and these are language which we use, and the biologists use. An interesting point here is this is already self-referential. The problem of self-referentiality, which in mathematics reflects it, is mathematics reflected by Gödel theorem. It built in the nature of biology. It's not, you cannot kind of separate it. And this is a big discussion when biologists speak about origin of life. What came first? Material aspect of that, namely metabolism. I say a few words about that. Or the origin come from information, and it was self-replication. And self-replication is not so much, it is of course carried by replication of physical matter, but replication of information is a genetic information which is being replicated. So what was the first step of life? We don't know that, but you know, they're inseparable in life as we know it. You can imagine artificial life where there will be no material structure. And when you look at the cognition, you see that material structure is replaced by something else, right? But information is number one, can be a new ingredient, number one new ingredient in life, and which will be, if you look at the history of evolution of life, it goes on and on. And this is a mind which beats the sword. Sword is a physical power, energy, physical energy, but eventually everything become taken over by information. Not completely, but up to a large extent. And so this is, and then there are higher level, just on the first level, when information appears, and this applies to what we speak about cells and subcellular structures. And this, of course, is the basis of life, from where we start. If to understand life, is number one, is understand the cells and what happens inside of the cells. Secondly, what happens outside cells, like ourselves. We build with many cells, a few trillions of them, and maybe you know that half of our cells, not ours, bacteria which lives in our guts, which is kind of fun to know. So we are actually community of organisms, and this is kind of nice to know. We are not never alone, unless with some horrible problem. But then life goes from stage to stage. When you go to the high level, it's not just cell, but more high level informations. They start, so from the cell, next level are multicellular organisms, which appeared probably 600-700 million years ago. I'm not certain this is well known. It's life as it is, we know it exists about 3.5 billion years on life, on Earth. But then multicellular organism appeared somewhat later, and then animals came, and then next level was when muscles and brain developed. They developed more or less simultaneously, and the main function of nervous system was control muscles. And this remains still the major factor, the major ingredient of our world perception. We cannot imagine it completely. People who has no vision, or those which have no hearing, blind, mute people, they still can perceive the world, and they develop language. They can learn language. They can write poetry, and there are precedent to that. But we cannot imagine a human being which has no muscle, nerve muscle connection. It will be a vegetable, literally a vegetable. So our major intellectual, or not functional by our brain or mind process, is our muscles talking to our brain. And by the way, I can say that you might think that for mathematician is kind of strange. We think which is something high level. There is an interview which Einstein, I think he gave it to Adamar about how he thinks, and he basically said something like that he thinks by his muscles, that his deeper mental images modeled by what happens in his brain related to his motion, right? It's vague images but related to motion, and there is a good reason to believe that our mathematical ability sitting in there, before it turns into words, it is in the part of the brain which control your muscles. Because really you have to solve a lot of mathematical problems when you move, and these are which we cannot even imitate in the computer, especially if you look at the kind of performance of people doing fantastic gymnastic feats. It's mathematically quite amazing, and we solve this. Also, animals like apes do that also. It's not accidental we came from apes, because motion of ape, if you look at the apes or just monkeys, how we jump from branch to branch, it's extremely complicated mathematical problems that I solve every second. Actually, when we walk, it also like that. You need a big brain, well, already for vertical walking or moving your finger, etc. So that's already interesting part of that. And then there is mind and languages, and which are a final product of that. So eventually we have to understand that. But when you go to this next level, this what I said, that there is a combined matter, energy, and information flows become insufficient, because there is no matter, right? When you say the working of your nervous system inside of your brain, or even when it goes outside of you, write something. Of course, your muscle work, but this your hand moves when you write something, on your tongue moves when you speak, but this is not of much essence. They're rather passive in this, right? They're not involved in this loop. Yeah, there is this for cells. You cannot separate information, how it being perceived, and the what carry of this information that go along, right? So information carried by by cells is about how these cells work, and cell carry macromolecular essentially cell carries information. So this is circular picture. It's not obvious so much, for example, the structure of human language and human mind. But so what happens here, my understanding is that there are several levels, a different level of structures. They're both now, from some moment on, they become pure informational structures, or mathematical structure, if you wish. So physical laws here not applicable anymore. Physical description doesn't apply to them, but they're on the bottom, and then on them, next level information structures emerges. And the question is to understand them, and hopefully some experience with how it works on the cellular level can suggest you, not it will be exactly the same, but the principle of evolution, the principle of life is just the same. Yeah? Life and evolution, which created us, are extremely primitive. Yeah, and there is this saying in biology that evolution is smarter than we are. But my point of view, we are stupider than evolution. Evolution is stupid. We are created in the most primitive and stupid way, and in the end, they give some examples demonstrating that, right? Our fantastic stupidity and comparing to evolution. So on page 2, I have 5, so I have 40 minutes. So these are cells. And there's just two, with general education, there are two kinds of cells. These are bacteria, and there are eukarya, which are what is called prokaryotes. They don't have nucleus, and they're relatively simple structured. Again, it's relatively extremely complicated. And then there are high level of organism like yeast in ourselves. Yeah, we more or less at this level, difference between us and yeast is minor. Yeah, but break from bacteria is tremendous, because there is an internal complicated structure here, and this is our cell is useful to keep scales, so to understanding the bacteria of the size of 1 micron. And of course, in the time of ancient time, and comprehension of that would be really kind of incredible. Yeah, this is a fantastic discovery of maybe 200 years ago, 100 years ago. People understood cells, and now we understand next level is subcellular level. So coming next, so inside of the cell, there are next bottom structures from where we can see what information is, what is structure is, and how they connected. Here is a piece of a cell membrane. And if you see this kind of fantastic physical structure, because there is protein sitting inside, in a second, We speak something about them. And again, every word indicates in there, it's a volume of knowledge behind it, because it's very schematic. But some of them are relatively simple. But again, mathematics of this is completely undeveloped. You have vertical rods, and so your membrane made with vertical rod kept together. And in particular, the same as you see in soap, more or less in soap films. And we have soap films, and we have this plateau and on minimal surfaces, But if you look what happens in the cell, what happens in reality, it's not one-dimensional, it's not two-dimensional structure, it's three-dimensional structure. And the basis of the structure is one-dimensional, it's vertical rods. So it's given by its normal bundle, it's material realization of its normal bundle, and they're kept together, not by any force. There is no attraction. They're kept by ambient interaction with the water. And so it is statistical object. If you heat it, it disappears. If you cool it down, it comes again. And this kind of mathematics of this is in non-existence. Non-existent, yeah. That's what we know. Physics to do with that, but you don't have mathematical theory of that. It's one thing. Now this, because the basis of that is physical. It's typical kind of physical problem, a mathematical problem in biology, which is not even paused and has not been much studied. But this basic simple structure, it's simple, but it's as complicated as the most complicated thing in mathematics. It's like understanding this, like proving Fermat theorem. But it's simple. But what is the next level? It's a ribosome. And this is a machine which reads your genetic information and creates you, basically makes you. It's a machine which creates your body, your essence, more steps, namely, it creates protein. And this is believed, justifiably, that the most complicated machinery in the observable universe. It was outside of our universe, which several hundred light years across. We can say it. Outside we cannot say it because we have no information. But there is reason there is nothing more complicated. Nothing complicated, at least on Earth, about what we know. Of course, this is a particular machine. And so what's remarkable, and this remarkable feature of this machine, as many mathematical, it appears in trillion, quintillions of copies. It's not alone. And a machine of this kind, everywhere, every cell, every organism on Earth, and there are about, I believe, 10 to the 30 bacteria on Earth, and each of them has hundreds or thousands of these ribosomes. So just to have an idea of their size, if we return to this picture, these little dots more or less give you an idea of the size. So there is about 50, I think, or 16 nanometers in diameter. So well below, of course, the size of 1 micron, about 100 times smaller, 10 times smaller. And this, again, an unbelievable thing that this such thing is possible. And yet also it must be understood, again, this is kind of physical aspect of that it is not stationary environment. It's everything moves. You see, on the level of one molecule, we have kind of Brownian world. Everything oscillates, right? And however, with fantastic precision, it reads what happens in your genome, and it is intermediate object. In a second, show this messenger RNA. And again, it's incredible logic of that, how things are balanced. And then this happens. And one problem is this indeed the only possible design of life? Granted our physical, of course, physical property of the world we live in. Of course, say at now a range of temperatures and pressures. Is anything else conceivably possible? There is DNA, RNA, machine like that, and, well, this is a kind of elementary blocks where chemistry kind of behind it, but this kind of little thing, which is size of probably on the level of a few angstrom. You can say even how much, yeah, maybe 3-4 angstrom size, even much smaller. This thing from which proteins are made. This is another picture, just what's happening in the cell. This is a kind of chemistry which is run by the cell. It's hundreds of chemical processes organized certain way. Again, this, by the way, most biologists don't know the detail of that. An extremely complicated process. Detail of this, well, very hard to learn, and it's because it's volume and volumes, and each point of that it was kind of Nobel Prize, and this Nobel Prize, and they not come cheaply, I must say. And this is kind of really bright people done that. But now look at the genetic scheme. What enters there? About information flow. So this is all about, essentially about material flow. Of course, they're not pure material. They're organized, they structured by different function of enzymatically, they're structured in a very tricky way, which I cannot time to explain. But more traditional, more transparent picture is this one. Make it included everywhere here. And this is a remarkable kind of point where mathematics maybe can enter this simple logic here. There is DNA, there's two strings of heterogeneous molecules linked together, and sometimes they divide. And this is one of the processes, which is not quite chemistry. It's kind of chemical process molecules. However, it's nothing similar in chemistry, which you know outside of biology exists of this kind. And then from which this string of DNA, you make a copy by transcription, what is called essentially the same molecule, essentially, but it's not the whole big. The DNA is huge, yeah. In you, each piece of DNA, its length goes in centimeters. The total length of DNA in your body about 2 meters. So it's huge, and each ingredient of that is just half of a nanometer. So it's a billion of them. But then you extract from them small part, which makes us just only several thousand units, molecules, and these are your genes encoded in RNA. And then this translated by this machinery of ribosome, again, it's incredibly complicated, interesting machinery, and you create polypeptide chains. And this is translation in a sense, because DNA and RNA written in 4 letters, there are 4 different molecules, and information encoded in a very Shannon kind of way, like in a Turing machine, a sequence of four symbols, and here is sequence of 20, sometime in fact 21, 22 symbols, amino acids. And one of them is shown there like that. And then miracle happens. And this is machine. They're complicated machine. They're horribly complicated machine. They do this incredible work. Okay, by other machines. He also is my machine doing this. That's a rather complicated enzyme. And how they work, of course, we don't understand the detail, but we know they're a machine, right? Like imagine how a factory doing that. But then miracle happens. You do this thing, it goes into right condition in an essential subject like water with something, and then out of the string, actual physical objects come from this protein. And it just falls because there are interaction between different pieces of that. There is a little interaction already between them. They kind of tend to stick here and here or here with different kind of energy. And then this things kind of creates a 3-dimensional shape like potato. Well, there are variations of that, but if it is typically 200-300, or between 1 and 300 units, these amino acid residues, the so-called residues for some reason, they're not already amino acids, but only what remains with them after they be brought together. They have this, what is described here schematically, but in fact, physically, it's at a ball size of a couple of nanometers, potato-like shaping, wrongly shaped. And what's important, it has some particular kind of empty spaces, little holes in there. It's kind of concavities. And this concavities is new way of information written on 2-dimensional space. You can think also about this as distribution of electric charge, slightly non-uniformly charged. And all this is written in this sequence. So you just, but who reads it? Here at your machines for doing that, your reading can do it. But there is nobody who reads that. It just happened by itself. It's called self-assembly. But what naturally by itself? Now, these things live in a Brownian environment, and it is being hit by these molecules, by essentially water. And it being hit by them, it just change, and takes the shape. But this is not supposed to happen. So this rough situation is like that. You know, chemistry of macromolecules, and the man who done it was first developed the theory was Fleury. There are 2 kind of great scientists, Fleury, and one was with chemists, and another was biologist, and both of them received Nobel Prize at some point, and maybe you alive, being now you in the audience, most of them, I think half of you alive only because second one was born, right? Which you are not aware of, I guess. But this is another Fleury who created this theory of random walks and this self-avoiding random walks. And he also created what now people call percolation theory. He invented these 2 theories. in chemistry, not in mathematics. He does infinitely more than we can imagine. But this, from what theories follow, this that doesn't happen. It just cannot happen. It cannot happen. And this is the following kind of similarity. When your physicists sometimes start speaking about law of sake, like Feynman or whatever, oh, everything is physical. We know everything or atom, we understand everything. And then just if you take the simplest example, like the basic physical law, everybody knows from the school that there is gravitation and all objects go, and this was articulated first by Galileo, that all objects go to the Earth essentially with the same speed. There is little correction, of course, with the air resistance, but if you have something of 10 gram or 50 gram or 1 gram in your hand, you drop it from your head and it hits the floor in a matter of half a second. And as physicists say, and this was actually articulated by Einstein, you don't need any theory, you don't need any expert. You make one experiment, the law is broken, that's it. And you take a bird, you open it, and it doesn't go down. And physicists say, oh, well, you have to do it in the vacuum, you have to do this, that. It's nonsense. You cannot say in language of physics what is a bird, what being alive. It may be not a bird, it may be human-made machinery, some kind of a rocket with a repulsion, which do the same in vacuum. You cannot say it in terms of physics. And in particular here, in this particular instance, it's very well known. If you look at the Flory theory and all this random walk, whatever, it applies to genetic systems. Physics applies either to highly symmetric or to generic, but certain particular system where physicists can talk about. They don't have even language to speak about proteins, truly, because proteins have a purpose. It doesn't fall just for fun. It falls and takes the shape for the purpose this protein making the cell and eventually build your body. And only very special sequences can fall. Most of them wouldn't fall. They make this, and sometimes in biology they didn't fall also for some reason not fall fully. But this is perfect violation of physical laws. Laws, because physical laws are not something that nature obeys, but the matter we speak about nature. And sometimes this law, anyway, it's a metaphor and misused. In a second, I give you another beautiful example how a metaphor was misused by one of the cleverest scientists of the century. So, and here is something else about communication, how information, there are cell signaling to ants talk by pheromone. Some say they also by touch. There is some controversy if they can actually count how many times they touch each other. And this is how people extend the ideas. Biologists sometimes call the meme, yeah, which we understand no better than this cartoon tells you. But yeah, but here there is a list of features of this information system or information meta system which we observe in life. Because I don't have much time, I just skip it. But I turn to this. So what is the relation between these two? Yeah? And so this Hogan was one of the kind of brightest scientists of the 20th century. If you take 10 or 20 scientists, he will be among them. Yeah, mathematicians usually don't know much about biologists. And it was said about him, if he didn't exist such a man as Haldane, he had to be invented. He was fantastically new. He was mathematician, he was biologist, he fantastically contributed to chemistry, to catalysis and everything. And he formulated this kind of nice sentence, which says, if my opinions come from chemistry, so it's logic of chemistry, by law of chemistry, but the logic must define my thoughts. And this is a beautiful example of misuse of metaphors, because laws of chemistry or determined or logic is meaningless words out of their proper context, right? Like law originally come from jurisprudence. It's a law what you have to abide by. It's not nature doesn't abide by any laws. Yeah, the way we talk about nature is just a matter of speech. Yeah, and this is a good example. And this is a kind of practical example, exactly explaining how naive what he was saying. So what we see here is ants and there is an end path, they follow some particular route, and they go from ant hill to the source of food. If they find the food, a big source of food, they pretty soon they go there many ways, but eventually find the shortest way. And it's always mathematical problem. I don't know whether laws of logic or any kind of laws, but they use chemistry, or rather the olfaction of pheromone, because you may be heard of that. They start go by many paths, but they follow the paths which have the most strong sense, smell of their pheromones, and the shortest path automatically develop stronger smell because more of them faster go there, and so eventually they all stick to the shortest path. This is a beautiful algorithm, and it's hard to say whether there. And this is it's not so what works in your brain, but they give you an idea what may happen in your brain. And here is a formula, we recognize it, due to Ramanujan. And the question is, can you find a model of this kind, invented, which might be very simple, very natural, like the one which I explained with ants, nothing extremely fantastically simple, in explaining how the formula came out of his head, or something, or everything else which came from his head. And unless you arrive at this point, you have zero understanding of human mind, right? This is a very simple thing, much simpler than everything we do in our life. But still we cannot explain even that. Now, so there is a kind of the end of that the parallel of what happens in learning and analyze how your brain work in the flow of information and transform it, which is similar very much, again, on generic terms, how, say, cell like of yeast exists in the external world, and how it modifies it and how it learns. And actually, a cell of yeast can learn many things in their life from this. I just said we have not time, and I just want to come to some end of that, because my time is limited. And so I want to come to the following. This is the main thing which enter, which should be presented. But you see, what I wanted to emphasize, one mathematical problem. Yeah, here. Here's mathematical problem, which may be heard in different terms. They present it slightly differently. So people travel around the universe, and each of them come, and then they come together from different planets, and they know each planet has particular deadly infection, and they all contagious. They may be contagious, but they can take vaccination and will be happy. And they have, all of them have identical, and there are 100 of them, 100 people from 100 places, and there are 100 known viruses, and they have to be vaccinated against them, and they have identical kind of boxes which contains information how to make this vaccine, or how to give, or where to find it. But the trouble is that this on the top of the box is not written, so I have to open it and see if it is for your virus or not. And so they have completely identical boxes, and they sit in their offices, and they're separated at the moment, and each of them is allowed to check half of those boxes and finding, he can find their name. And if they find the name of their vaccine, of their virus, then they know what to do, and they will be cured, and everything's fine. However, if at least one of them will fail, and I repeat, the 100 of them, they can try whichever 50 out of 100 boxes. If they find the right box with their virus, they're cured, and that's it. If not, they're infected, and when they come together, all die. So they must be careful. Each have to find the right one. The question is, what's the probability? And they can, of course, talk to each other, but they only talk at the very beginning. And they talk even before they started all this story. They already agreed about what to do. They know what to do. They don't communicate. All communication before they came to the stage. What's the probability? If they behave in optimal fashion, that each of them find the right box, and they all will be vaccinated. And of course, from physical point of view, probability eventually is zero, right? Because finding correct thing out of 50 is about 1/2 to 1/2 to the power 100. It's very small number, and maybe you can do a little bit correction, but still it comes like 0. And so the physicist answer, it is 0. But biology answer and life answer, yeah. And if you make correct algorithm and you guess it, and the nature can guess it, it's about 1/3. With probability 1/3, they can each of them find the right one. And this is a difference, mathematical kind of mathematics involved in physics and in biology. So this is, maybe some of them don't know this problem, and you heard of that, and then it will be not so fun. But if not, you can think about that. What are the algorithms which say you can, each of them can check 50 out of 100 and find one single which is adequate. The probability for it looks like for one is 1/2. See, it's no better. But for 2, 3 more, it's only 1/3. It doesn't multiply. So for a physicist, if things are not obviously related, they're independent, and you compute probability by multiplying. In biology, things are correlated. Biology makes things fantastically correlated. And they say, we thought that it's fantastically correlated. And you need completely different set of mathematical and mental setup to do this. And so these are examples, which I didn't explain many in biology. There are billions, for example, of biology and in human cognition process, which show that. Okay, so I stop there. And I don't know if there is any possibility of questions.